All right, I promised you some examples on how to perform these emission spectrum calculations. So above what you see is all the information I provided for you in class. You're not going to need to memorize any of this, but you will need to know how to use all of it. So the first example is written below. It reads, what is the wavelength in nanometers of light that has a frequency of 6.17 times 10 to the 14th hertz? All right, in class I asked that the first thing you do is highlight and label the important information that the question provides you. So when I read the question, I notice that it's asking me to calculate wavelength. So I'm going to highlight wavelength, and I'm going to put the symbol for wavelength above it, which is the lambda symbol. The next thing I notice is that the question provides me with the frequency of that light, which is 6.17 times 10 to the 14th hertz. Okay, I need to figure out which formula to use. So I look at what the question provides me. It gives me the wavelength, and it's asking for the wavelength actually, and it gives me the frequency. So the equation that makes the most sense that we're going to use, if I look at the above equations, is the first one, for the speed of light equal to the frequency times the wavelength. Alright, so once we know what formula we want to use, we want to write it below, and we're going to list out all the information that we know. Okay, wavelength is obviously what it wants us to solve for, so that's our big question mark. That's our variable x. C is equal to the speed of light, and that's a constant. It's provided above. It's equal to 3.00 times 10 to the 8th meters per second. And lastly, the question provides us with the frequency of that light, which is 6.17 times 10 to the 14th hertz. Alright, so I have all the information that I need to solve this problem. The first thing I have to do, however, is rearrange the equation to solve for the variable wavelength. So when I rearrange the variables, my new equation below is going to read wavelength is equal to the speed of light divided by frequency. Alright, the next thing I'm going to do then is plug in the variables. So since the equation is wavelength equals to the speed of light divided by frequency, I'm going to plug in on top my speed of light, which is 3.00 times 10 to the 8th meters per second, and I'm going to divide it by the frequency that was provided for us in the problem, which is 6.17 times 10 to the 14th hertz. I plug all these babies into the calculator, and what I end up with as an answer for the wavelength of light is 4.86 times 10 to the negative 7th meters. So I've solved for my wavelength. It's 4.86 times 10 to the negative 7th meters, but the question asked for me to provide the wavelength in nanometers. So there's one additional step that I need to do. I need to convert 4.86 times 10 to the negative 7th meters into nanometers. So the final step is going to ask me to perform dimensional analysis. I need to convert meters into nanometers. So if I look up in where it says important conversions, I notice that the conversion between meters and nanometers is 1 meter is equal to 1 times 10 to the 9th nanometers. So I need to set up my dimensional analysis. I always put my given over 1, my goal unit goes on the top on the other end, and my given unit goes on the bottom. So in this case, my given is 4.86 times 10 to the negative 7th meters. I'm going to put that over 1. And on the other end, my goal unit goes on top, so nanometer goes on top, and my given unit, which is meters, goes on the bottom. I then plug in my conversion in the appropriate spot for the conversion, and then I multiply across and divide down. So I'm going to multiply 4.86 times 10 to the negative 7th meters times 1 times 10 to the 9th nanometers, and I'm going to divide it by 1. Again, my meters are going to cancel out, and what I am going to be left with is 486 nanometers. That is the wavelength in nanometers, which is what the question asked me to solve for. So ta-da! That's my final answer.